we present our work on a hierarchical deliberative-reactive system architecture for task and motion planning in partially known environments. Solving complex tasks with highly dynamic robots like the Minotaur quadruped robot is challenging. This usually requires planning and execution of dynamic actions, such as walking, jumping, and manipulation of objects, usually in cluttered environments with static and movable objects. Hierarchy is essential to solving these types of problems, and it is well understood that abstractions are required to do so in a computationally practical manner. Some techniques include reactive layers that account for worst-case scenarios under uncertainty, or decomposing complex planning problems into a hierarchy of sub-problems at varying levels of abstraction. State-of-the-art solutions to these problems usually combine fast, discrete symbolic planning with sampling-based discretizations of continuous action spaces. We propose a system architecture that provides its own abstraction and formal guarantees for task and motion planning. Specifically, we combine prior work in a hierarchical system which contains a deliberative planning layer that accepts a description of the world and reasons over abstract actions to solve complex tasks, a reactive layer in the form of a vector field planner that can guarantee target convergence even with unanticipated obstacles, and a gate layer that uses high-rate feedback control to execute navigation goals from the upstream layers, such as velocity tracking and target behaviors like jumping or grasping movable objects. We are interested in solving problems involving navigation among movable obstacles. In our work, we define the environment as a set of polygons with planar poses in SE2 as well as vertical heights to reason about jumping. We plan using a domain description with abstract actions mapping to dynamic behaviors. These actions have parameters, which can be discrete, for example a particular object, or continuous, for example a target pose. The deliberative layer searches for a valid sequence of actions with instantiated parameters that can solve a given goal specification. In prior work, which we use as a baseline, the deliberative planner performs integrated task and motion planning using simple straight-line motion primitives. The feasibility of actions is thus determined by evaluating collision checks between sampled poses. Resulting plans consist of potentially long sequences of actions. The reactive layer is only used locally for tracking of the resulting path and handling unexpected obstacles along the way. In this work, we propose a system that uses the reactive layer globally to delegate metric details to layers below the deliberative planner, without losing guarantees of correctness and probabilistic completeness. Instead of sampling motion primitives, we leverage the contract offered by the reactive layer, specifically that the robot can navigate anywhere within its current connected polygonal component. This means that abstract actions are now associated with transitional behaviors. That is, we're directly planning to perform tasks like jumping, grasping, and releasing on any object that is topologically adjacent to the robot's current component. So we can now express the plan as transitions. First to grasp the red box, then to release it at a different location, and then to jump on the box on its way to the elevated goal. This abstract plan consists of less actions, and the deliberative planner does not need to know how these transitions are instantiated by the reactive layer below. This leads to significant computational savings, as we show with numerical experiments. For example, here we explore planning in increasingly cluttered environments. As the environment becomes more complex, the local reactive planning approach requires a larger number of samples to successfully plan by checking for collision-free straight-line motions. Our global reactive planning approach allows expressing the plan as only two transitions, first to establish contact with the red box, and second to place it in the goal. While our approach is topologically unaffected by clutter, and can plan with a modest number of samples while guaranteeing correctness, we still see an increase in computation time from polygon calculations. In this simulation, the robot attempts to reach a goal. Normally, the optimal solution is to traverse a hallway and directly move to the goal. However, as the hallway becomes more cluttered, the local reactive planning approach may fail to find a solution, and instead choose a suboptimal plan to move an object that blocks an alternative but longer path to the goal. Our global reactive planning approach can consistently find the shortest path so long as the topology of the world does not change. For example, if we place a large obstacle that makes a shorter path completely infeasible. Our system can also solve complex tasks that combine all the behaviors we want to test: robust navigation in clutter, manipulating movable objects, and performing dynamic jumps to reach target locations. In summary, we propose a system architecture for task and motion planning that combines a sampling-based deliberative planner with a reactive planner. The contract offered by this reactive layer enables the deliberative layer to delegate metric details and plan at a more abstract level without sacrificing correctness or probabilistic completeness. Thank you.